Hi everyone, so today I want to talk about how we can find the limit as x approaches 0. Specifically from the right hand side, this is going to be important because the domain of the natural log function is from 0 onwards, or I should say a very small number after 0, or written like this I suppose, which represents the domain for ln. So of course we're looking at x ln x. So how exactly do we go about finding this limit? Well, when we evaluate a limit algebraically, we just plug in for x and ln x, and we're going to find that this is 0 because what's it called? Times zero. If I could English, x evaluated as 0 is 0, and then ln of 0 is negative infinity, right? When we're taking the limit, it's undefined at 0, but it goes towards infinity, right? It's doing this. So here's the y-axis, it comes up, and it shoots off that way. So, knowing this is an indeterminate form when you have 0 times negative infinity. But L'Hopital's rule doesn't apply here. And if you remember L'Hopital's rule, basically if you have an indeterminate form of, if I could pick red, of 0 over 0 or plus or minus infinity over plus or minus infinity, well then you can take a derivative of the top function by the bottom, and what that will give you is what the limit's equal to. And why this works is actually kind of cool, and I want to explain it because it's important that we explain it. Let's say we have x squared over x squared, and I was to find a limit of this. Now, of course, we know that this would simplify to 1, and thus the limit would be 1. But let's say, hypothetically, that it was indeterminate for whatever reason. Okay, let's do L'Hopital's rule on it. It's going to be 2x over 2x. Now, obviously, the limit is still 1, but notice how these quotients that we're making are quite literally just ratios. And when we take a limit, that ratio holds true because it's the same x junk over the same x junk. And when we plug in, when we do take the derivatives of L'Hopital's rule and then plug in 2x all that junk, 2x all that junk, it's going to simplify to that ratio, which we would have found here. But of course, because of some domain or syntax error, we weren't able to see it. So we go from indeterminate to determinate, right? Using that logic. So let's go ahead and do that. But you might be asking yourself, well, this is an indeterminate here. This is a weird indeterminate form. Okay, it's not in the quotient form of 0 over 0 or infinity over infinity. Well, we can make it that way, and to do that, we're going to take x over here, we're going to bring it to the denominator, and we're going to reciprocate it. So we're basically saying the same thing when we say the limit as x approaches 0 from the right side for ln x over 1 over x. Notice that this is the same. Be very careful here. You need to understand that this is saying the exact same thing, right? This, if we brought it up to the numerator and reciprocated it, it would be the same, right? So remember that these rules that we learned from algebra still apply here, even though we're in calculus, and calculus is more cool. It still applies here. So 1 over x in the denominator, it'd be like saying, okay, we have 2, and then we say, oh, no, I'm going to express that as 1 over 1/2, or 1 over 0.5. It's the same thing right there. They're equal. So we do that, and when we plug in 0, we get a new form. ln of x approximated at 0, or the limit of 0 of that, is still infinity, or negative infinity, technically. But the bottom, if you don't know what 1 over x looks like, just remember my favorite dance move, the 1 over x, right? So there's that horizontal asymptote at 0, and we go, whoop, right to infinity. But if we're coming from the right, and that's another reason why we denote that we're coming from the right here, we're going to infinity. So this is negative infinity over infinity. Still indeterminate, but now we can do L'Hopital's rule. So let's do the derivative of the top, which is just 1 over x. And then we're going to put that over the derivative of 1 over x. So x to the negative 1 is going to turn into negative x to the negative 2. So negative x to the negative 2. Okay, and what we can do now, and of course we're taking the limit, so I'm just going to put that there. I always forget the limit notation, so we'll put a little baby limit. So this is the limit as x approaches 0 from the right. So we're going to have, I'm trying to think. Yeah, no, that works. Sorry, I was just confusing myself. Negative x over x squared, which will then simplify to limit as x approaches 0 from the right and we can just cross out one of the x's, is going to be negative x, which 0, 0. So, isn't that pretty cool? We were able to determine that the limit, although initially in an indeterminate form, we turned it into a quotient. We took a ratio of the two products that we're multiplying together, and then we manipulated that to get a L'Hopital's rule idea, make that ratio, right? Take a derivative, which keeps the ratio the same, and then it just makes that limit a little easier to see, which we find to be 0. And this is true. I believe that this function looks as such, if you're curious. Like we have the x and y plane here. I believe it starts at 0 and it goes like this. I should know that, but I don't. But it starts here at 0 because, remember, it's undefined. Well, there's a hole here. I should put not a dot, an open circle. It's undefined there, but everywhere else in the positive x direction for all domain bigger than 0, it's defined there. So kind of an interesting problem. I thought I'd just make a video on it just to explain it. But that's going to be it, guys. So have a wonderful day. Bye-bye.